All right, here we go. Video number 2. End product inhibition. One of the ways your body controls, again, what it needs, making it only as needed. It's kind of like the shipping fiasco this year, where there weren't enough products because disruptions in the supply chain. Most stores don't hold a lot of stock. And your body doesn't either. It just doesn't want to keep a whole bunch of extra chemicals or molecules around when they're not needed. So end product inhibition helps with that, because what happens is if you have enough of a product, which would be D, it goes and blocks that first enzyme in the metabolic pathway, so no more is made. And that's called negative feedback. Meaning, if you get something of this, if you get this product, it blocks the production. Positive feedback would be if you get the more of this product D you get, the more activity in this metabolic pathway. But these are all different enzymes. So enzyme A, we'll call it enzyme B, enzyme C. Sometimes on the IB exam, I've seen the question a couple times where you'll got to figure out, well, where is this, the end product going to affect? Is it going to block this enzyme going from product A to B, or this enzyme B, or enzyme C? And just think about, in terms of energy, your body doesn't want to expend any of this energy if it already has it. So the most logical thing is to block the very first enzyme in that pathway. That way the body can save itself all the trouble on the energy, and the molecules are used up in making those intermediates. So here we have application. You have in your body threonine being converted to isoleucine. And once you have enough isoleucine, it'll come and block that first enzyme. So that threonine will stay as threonine. It won't be converted through all of these different intermediary products. So this is enzyme 1. Oops, let me get it. Enzyme 1. Oh my goodness. Enzyme 1, and inhibits it. All right, isoleucine goes down over here, blocks it, boom. So then none of this happens. Don't get any of this, because you already have enough isoleucine. So your body's like, forget about making more. This I mentioned before, way back in video 1. Bioinformatics. Opening up a whole different way for researchers to, look at these metabolic pathways, testing drugs, testing medicines out, using this genetic database of RNA, of DNA, of protein, to see what kind of, effects these chemicals have once we apply them. So research into metabolic pathways, chemogenomics. Okay. Chemicals, the way they bind to different enzymes, very complicated and tough to suss out in the bench, in a laboratory experiment. So this can really speed things along. Now, basic science takes a while really to come to fruition sometimes. So hopefully this will speed up in the near future. By the time you're my age, there'll be a lot more targeted drugs. Right now, it's still, when doctors prescribe medicine, they really don't know how the side effects will affect you as an individual. Maybe in the future that will be alleviated by, knowing exactly where these target sites are, when you use it, when different drugs are used. Malaria is one disease that still affects and kills millions of people every year. Wish I had the exact number off the top of my head, but I believe it's in the millions. and it's caused by a pathogen. It's a protist. It's not virus, not a bacteria. It's this funny little protist that uses the life cycle of the of you and the mosquito to grow and give these symptoms. I think it's 20-30% fatal depending on your condition, but it's become resistant. All living things are subject to natural selection, and this drug in the environment, this chloroquine, basically makes more and more resistant malaria. So the genome for this pathogen has been sequenced, and it can create models and then see if these different chemicals can inhibit the metabolism. Because remember, all of life, it's based on metabolism and how energy is processed. So if they can find a drug that can interfere with that metabolism, those pathways that we just talked about, you're really onto something. And there's one study that shows that new chemicals inhibit enzymes. And then 15 chemicals that it says bind to 61 different malarial proteins. So hopefully, by getting in there and interfering with the way this pathogen, goes through its metabolism, it can be pushed back. And if you could just inhibit that metabolism a little bit, your body has a better chance at clearing it. Your own immune system kicking in. And that's one thing. Cyanide, you've heard of cyanide poisoning. What cyanide does, it shuts down your mitochondria and shuts down cell respiration, and that's what kills you if you're poisoned with cyanide. You guys have probably heard of cyanide. So we need to practice calculating rates of reaction. We did this in an experiment. Junior year, we do this with potatoes and hydrogen peroxide. So we're going to do a little practice with this data again, kind of show you, we got to practice this. You just got to practice it to get comfortable with it. So say we did our experiment. We took our initial mass of our potato in peroxide solution with the beaker. It's 80.12 grams, and then you'll see it decreases slightly over time. So the first thing you need to do is calculate the mass decrease. So I want you to please get your phone out, like I'm getting my phone out right now, and do it with me, please. You gotta do this. You gotta just go through the motions. So I'm putting 80.12. Oh, maybe I can check it out. Ooh, fancy. There we go. So I'm going 80.12 minus 79.16 gives me 0.96. So I'll write down 0.96. And from 5 to 10, got 79.16. And it's so easy to make mistakes. You just gotta go slow. Minus 78.68. Oops. That's 0.48. And we have 10 minutes to 15, so 78.68 minus 78.43. If you see me doing something wrong, oh, I guess you can't tell me because it's taped. Oh, what was that? 0.25 0.25. So the difference, looks like the difference is decreasing. You always want, you know, whenever you're doing stuff, look for trends and patterns, whatever you're doing. Then we got 15 to 20, so 78.43 minus 78.23, 0.20. Last one, 20 to 30, so 78.23 minus 78.05, 0.18. Oh, by the way, I think yours, if you're watching this year, your numbers will look different on the one at home. Just, I made a mistake. Just put these numbers in your table right here, scratch out the old ones and put those in. So now we need to convert that to milligrams. So milli is 10 to the 3. So we're going to move our decimal place 3 places right or left, and we're going from a large unit to a smaller unit. Remember, BSR's big unit to smaller unit, move to the right. So here we have the bigger unit being the gram, smaller unit being milligrams. We're going to move it 3 times to the right. So 1, 2, 3. So this is going to be 960, 480, 250, 200, and 180. And those are kind of easier to deal with than the decimals. You know, when you're looking at decimals, not that difficult, but whole numbers are kind of easier sometimes. Well, usually. Now we gotta get our rate for milligrams per second. So we had 5 minutes. How many seconds in each minute is 60? So I'm just going to take 5 times 60. 5 times 60. That's 300. So I'm going to divide all these numbers by 300. So 960 divided by 300. That's what I'm going to do for all of these. So let's check this out. Get my thing here. So 960 divided by 300. There we go. I think that worked. 3.2 seems right. Yeah, and always kind of see if the numbers seem right. That seems about right. 960 divided by 300, a little over 3 times. Check it on your sense-making device, which is your brain. 480. Well, our brain can be tricked, of course. So we gotta always check on that. 1.6 times, and that definitely checks out, making pretty much good sense. 250 divided by 300. So now we're going to definitely be a decimal now. 0.83. I'm just going to add another significant figure there just to keep it. So we have down to the hundredths. Now 200 divided by 300. I might be breaking significant figures rules, but luckily in biology we don't have to worry about that too often. It's one of those sticking points in chemistry, pain in the butt. How many is that? 0, leading 0, significant figure? No. 180. 180 divided by 0, 0.60. All right, so now we have our data, and what we want to do, like you'll see in this, we're going to put the time on the x-axis. Normally it's always on the x, and then we're going to put the rate on the y. So here we have our 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 30. And they're all evenly spaced out in time every 5 minutes. So what we can do is just kind of space those out. We can go ahead and start here in our first. This is 0 to, let me change the color up there. We'll put this will be 0 to 5. And let's go ahead and skip 4. We won't have to look in between. Let's skip 5. It's easier if it's 4, but that'll use more of our graph. There's our 5 to 10. 10 to 15. I think that'll work. 15, 20. It won't work. Sorry. Sorry about that. We do need to do 4, I think, to fit it all. Thought I figured that out, but obviously not. So this is our 0 to 5. And then we'll go 4 spaces. This will be our 5 to 10. 10 to 15. 15 to 20. 25 to 30. There we go. Maybe it would have fit. Sorry about that. 0, 5. I messed up on that one. 20 to 25. And then 25 to 30. Okay. So that's spread out. That looking good. All of our data points are evenly spaced, which they should because they're even time increments. Now let's look at our y. So we need to go from 0 up to 3.2. So a little bit more than 3. So let's take a look. It would be good to kind of, for each, like start at 0. When we go here, if this is 1, that's pretty easy to estimate in between. So can we do that 1? So 1, 2. Yeah, that'll work. So that'll be 1. This will be 2. This will be 3. And since we have, it's spaced into 4 between 2 and 3, like 2.5 is right there, 2.25 is there. So that'll be easy to figure out. So this is rate in milligrams per second. Okay, that's really hard for me to write that way on this. So let's go ahead and do it. The first one, 3.2. So we start here, go 3.2. Let's go ahead and put 4 on there and make it easier. So 3, here's 3.25. So 3.2 will be right about there. Our next number is 1.6. Here's 1.5. 1.75. So 1.6 be about right there. Yeah. 0.83. Here's 0.75, 0.83 be about right there. And 0.67. Here's 0.5. Here's 0.75. 67. Something about right there. And then 0.60. Something about right there. So I'm going to try to draw this kind of line, kind of connecting them together. There we go. So that's our rate. We plotted it. Oh, I make sure, big stickler for labels. So this is the rate of mass decrease. Oh no, the rate is up there. Sorry. This is time in minutes. Sorry. In our minute, I just put time interval in minutes. Time interval. And there we'll have rate. I probably should add mass decrease, although we can see that in the data that it definitely decreased. So here's another thing you need to know how to do is looking at a graph like this, figure out what the normal enzyme rate is. We see a high rate, and that kind of levels off. When you have a competitive inhibitor, it'll decrease the rate, but it'll be pretty similar. You'll end up at the same. You'll see the same. You'll eventually reach the same rate, the same level of reaction. Same rate as without inhibitor. The big difference is this non-competitive inhibitor. It definitely decreases that rate, so the rate is lower. It does not. Does not meet rate without inhibitor. So you say, what's more detrimental to a reaction in terms of having it get done? Is that non-competitive inhibitor. Definitely decreases that rate much more than the competitive inhibitor.